This is 5.1.2, current voltage characteristics. So, first of all, if we want to investigate how current and voltage of a component relate to each other, we need to set up a circuit where we can get different values of voltage and current across a component. So a simple circuit to obtain a range of values for I and V So to do this, we need some sort of power supply. Then we have a variable resistor. And then we leave a gap for a component. And we put an ammeter and a switch. Now this gap exists so you can put your different components in there. So insert component here. And your components could be, for example, an ohmic resistor. It could be a bulb. It could be a diode. And then to measure the potential difference across that gap where the component would go, we put a voltmeter in parallel. For our variable resistor, we could vary this, e.g., for example, a 10 to 100 ohm variable resistor. So it could have a lowest value of 10 ohms and a highest value of 100 ohms. Now you can have different ones. It could be 10 to 100. It might be 100 to 1,000. It might even be something like 100 to 10,000. So you can get lots of different values for these. Now, this circuit has a limitation. So from GCSE, you know that the potential difference in the circuit will split up according to the components in that circuit. So we have a cell or a battery or even a power supply. That power supply will be adding potential to that circuit. So for example, it might be 6 volts in. Now when we jump over any components, so the variable resistor and the component we're going to put in the gap, we're going to lose some potential difference. So if the variable resistor is set to a high value, then it's going to take more potential difference at the variable resistor, and there's going to be less potential difference left for our component that we insert into that gap. Now if we set our variable resistor to its lowest value, which is 10 ohms, it still has a resistance. So we can never get, in this circuit, we can never get the maximum potential difference across our component. For example, we put a bulb there, we can never get 6 volts on the bulb. Because the variable resistor will always take something. Even at its lowest value, it's still 10 ohms, it will still take some voltage. And likewise, we set it to 100 ohms, well, the voltage will still split between the variable resistor and our bulb or our ohmic resistor, so we will never ever get a zero potential difference. So we'll only get values in between. So that's the limitation of this circuit. So a better circuit to conduct the experiment would be to use a rheostat or potentiometer to act as a potential divider. Now this is going to make the circuit look a little bit more complex, but we'll explain how it works. So let's set this circuit up. So we still have a power supply of some sort. And we have our potentiometer or our rheostat. Set up like so. Then coming parallel from its slider, so these have sliders, we have our gap with our component and our ammeter. And then we put our voltmeter in parallel to that. And in that gap, we insert component over there. Yeah. I will show you that later on. No, this is now called a rheostat or a potentiometer.
So is it just like a normal resistor?
No. No. It's called a rheostat or a potentiometer.
Oh.
That's why it's got the arrow coming out of it in the center. That's a slider. Now, I want you to focus on that slider, yeah? Which is the arrow here. So this is a slider. I can adjust this slider by either sliding it all the way to the left of that rheostat or all the way to the right of that rheostat. Let's say that this rheostat is maximum 100 ohms. Yeah? If I slide it all the way to the left of the rheostat, then the entire 100 ohms is going to be in parallel with our component that we want to measure. And in parallel, components have the same potential difference. So if I'm supplying 6 volts from the battery or power supply, that rheostat will have 6 volts across it. Because our component will be fully in parallel with it, then we will have 6 volts also across our component. So we've got the full 6 volts. If we leave it completely halfway, then we've essentially chopped the rheostat in half, that where the left-hand side is 50 ohms, and the right-hand side is another 50 ohms. So the left-hand side of the rheostat will get half of the potential difference, which is 3 volts. The right-hand side of the rheostat, 50 ohms, which is half the resistance, gets the other 3 volts. And our component is in parallel with only half of the rheostat. So we get 3 volts on our component. And the final thing I want you to imagine, if we slide that slider all the way to the right, that means that our component now is not in parallel with our rheostat, but it becomes in parallel with this section of wire on the right of the rheostat. So the rheostat gets the full 6 volts. Our component is parallel with a wire. The wire has no resistance, so it's a short circuit. So the wire has 0 volts. Our component is in parallel with a short circuit, so our component has 0 volts. And therefore, no current flows through our component because current will take the path of least resistance and go straight back to our power supply. So in this way, we've got the full range of 0 volts all the way to the maximum that our power supply can provide. Now, if we want to get negative values of potential difference in current, we can simply just take our power supply and connect it in reverse. Yeah, or take out a component and connect it in reverse. The easiest would be to reverse the power supply.
What is this doing exactly?
Measuring current, measuring voltage.
Yes.
Different values
Of components.
of a component that we put into that gap. Now, we do that with an ohmic resistor. Start a new page, please. So if we put potential difference and current, for an ohmic resistor, we will obtain a straight line which looks like that. So the explanation here is, assuming that the ohmic resistor remains at constant temperature, current is directly proportional to voltage. So we say that I is directly proportional to V. To get rid of the proportionality symbol, we can put an equal sign and some constant. If we rearrange that, we get V equals to 1 over some constant times by current. And 1 over K is equal to resistance. So we've got V equals to IR. And that's Ohm's law. Now, we'll move on to a bulb. So the results for a bulb will give us an S-looking shape. I didn't do a very good job of drawing that, but I can move it slightly. It's a bit better. So again, the axes are current on the y-axis and V on the x-axis. Now, at very low potential difference, we have a very low current. And so at that point, the bulb is at constant temperature. And at this point, you won't even see it glowing. But at very low potential differences in currents, the bulb is at constant temperature or near enough, approximately constant temperature. So if it heats up a tiny bit, it doesn't really make much of a difference. And so if you look near the origin, it looks almost like a straight line. But as potential difference increases, the current increases. As current increases, the temperature of the bulb increases. As temperature of the bulb increases, the atoms in the lattice vibrate more. And as those atoms vibrate more with higher amplitudes, it becomes increasingly difficult for electrons to pass through. And difficulty of electrons passing through means more resistance. More resistance means less yielding current when you continue to increase potential difference. So it curves. And it curves where you continue to increase the potential difference, but current doesn't increase as rapidly anymore because resistance has increased. So let's write that down as bullet points. At low potential difference, the bulb obeys Ohm's law. And I'll put in brackets, not yet glowing. Because something that glows means that it's very hot. Then we'll say that as current increases, the filament in the bulb, so the filament gets hot. If the filament gets hot, atoms in the lattice vibrate. Atoms in lattice vibrate. Now we have to be careful here, is when we talk about vibrations, are we talking about how fast they're vibrating or how far apart they're moving from each other? So in this case, we're talking about how far apart they're moving from each other because the lattice is always vibrating anyway. The atoms in the lattice, they're always vibrating. But now they're vibrating with a bigger amplitude, so they're moving more. So atoms in lattice vibrate with greater amplitude making it more difficult for electrons to flow, or for free electrons to flow. Therefore, resistance has increased. And if resistance increases, then that means that you get less yielding current per increase in potential difference. So results in lower yield in current per increase in potential difference. And then we will move on to the diode. Similar sort of graph again. So again, we'll put current and potential difference. Now, a diode actually has two sides. The forward bias, where you connect it facing the correct way, and the reverse bias, when you connect it backwards. And they behave differently in these biases. Now at GCSE, you would have not looked at the reverse bias much. So I'm going to add a bit onto that you haven't seen before. So with a diode, At very low potential differences, you have no current. So we start from the origin. We increase potential difference slightly, and we still have no current, until we reach a certain potential difference here. And once we exceed that potential difference, current then increases very rapidly. So this value here is the threshold potential difference, which could usually be about half a volt. So it's a very small potential difference. Beyond that, the current increases so rapidly that if you put any significantly more, like for example, if it's rated at 1 volt and you put 2 volts, 3 volts, expect that diode to burn out very quickly. Because the current goes up so quickly, it gets very hot very quickly and it will burn out. Now, if we put our diode in the reverse bias, so we put negative potential differences on it, then it continues to be 0 for a long time until it gets to a breakdown voltage, and that allows a reverse current to flow. But you need much greater potential differences for that to happen. So the explanation for this is diodes only allow current to flow in one direction. At small potential differences, and I'll put in brackets, less than threshold, in forward bias, no current flows. At greater potential differences, than the threshold, current increases very rapidly. And then the last bit we'll add on to that is in the reverse bias, much larger potential difference is required to make current flow. And then on this graph, we'll just label this as a forward bias and this side as the reverse bias. And that's the end of 5.1.2.